Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD student at IIT Palakkad. Today we are going to discuss the summary section of the week 12 because in week 12 there is some of the theories and some of the problems need to be covered. Okay, and some of the in general questions I taken from the other weeks, the theoretical questions. Okay, and one problem from the uh, week 12 section. Okay, it will be a 1 hour section. Okay, so let's start the section. So the first question is the reaction turbine is also called as dash. So the answer is C. Yeah. So the reaction turbine invented by person called as Parsons turbine. Okay. Yeah, let's go to the next one. So the compounding is used for dash power applications. Okay, compounding always done for the high power applications. Okay, because in single stage it's not possible to generate that much power required for a compressor. So staging and compounding are in a gas turbine engine is required. Okay. Compounding is produced at low speed. Okay. So this can be also a question. The compounding produced what kind of speed? It's produced at low speed. Okay. Without compounding, the speed will be high, but the cost it pays is the speed will be lower. Okay. In velocity compounded turbine, flow passage is from dash. Okay. So all these options are actually wrong. Okay, these kinds of question you can expect. Okay, where you will expect one option to be correct and you just choose, and in exam especially maybe all option can be wrong. Okay, so your answer is actually D. Okay, so for the velocity compounded turbines, flow passage is from fixed nozzle fixed nozzles to multiple rows of moving blades and alter alternating with fixed blades. Okay. So in the questions, so the fixed in the options, either it's moving blades written, or or in the question there is no term about fixed blade that it didn't mention. So B option cannot be a correct choice. Most of the people will choose B option, which is a wrong option. Okay, this is both fixed blade and moving blades. A velocity compounded impulse turbine is also called as dash. This velocity compounded turbine is invented by Curtis and named as the Curtis wheel. A turbine comprising of fixed blades and moving nozzles is called as reaction turbines. A true statement. So what does this reaction turbine means? The reaction turbine means the reaction produced when steam hits the turbine. Is also used to produce work output. Okay. Which will be the input in the compressor. Okay. The losses occurred while passing through blades are called as dash. So whatever the loss passing through blade, obviously this mostly due to the friction, that it will be a frictional loss, blade friction loss. Okay. The friction between blade and steam. For fixing blades and rotating components together, dash are used. Okay. Okay. So the answer is glands. Okay. These terms are very important. Okay. It's required to be remembered. These glands, all these things. Used to fix blades and rotating components together. The losses occurred at the gap between the glands are called obviously the gland losses. Okay. The kinetic energy that steam has while coming out of the turbine is called as dash. Okay. Okay. That means the whatever the steam coming out of the turbine is actually kind of what? A kind of residue. Okay. So we just tell it as a residue loss. Okay. Or residual loss. Okay. The loss that steam contains while exiting the turbine. Okay. Called as the residual loss, and this energy in the residual loss cannot be used unless some special arrangement we will make, like uh, turbocharge or all these types of arrangement. If you do, then only we can reduce this residual losses. Okay. This energy cannot be used. in general, this energy cannot be used. Okay. Okay, so this is the question taken from the lecture 12. Okay. So yes, the question is a single stage axial flow turbine operates with an inlet temperature of 1100 Kelvin and a total pressure of 3.4 bar. The total temperature drop across the stage is 144 Kelvin and the isentropic efficiency of the turbine is 0.9. The mean blade speed is 298 meter per second and the flow coefficient is 0.95. The turbine operates with a rotational speed of 12,000 rpm. If the convergent nozzle is operating under choked condition, then determine the blade loading coefficient, the pressure ratio of the stage and the flow angles. Okay. In the right side we can see the stator or the nozzle and the rotors. Okay, with all the stages are given. Okay. Okay, so let's start solving. Okay. So yeah, so the first bit is the blade loading coefficient. Let's find that. The blade loading is defined as psi is equal to psi equal to Cp into delta T naught by U square. Okay. So in the question, okay, so the Cp is not mentioned. Okay. Just if it is not mentioned, just assume it as a our standard value. Okay. So let's take the Cp this value. Okay. Okay, for the inlet temperature of 1100 Kelvin, they should give the Cp value. Okay. So the Cp I will write down from the table. You can find out this value. 1100 Kelvin here 1148 joule per kg Kelvin. Okay. And then the delta T already given the stage is 144 Kelvin. Okay, the total temperature drops across the stage is 144 Kelvin, and uh, the mean blade speed is, okay, the mean blade speed is 298 meter per second. Okay, that means you also mention, okay, temperature drop and is 144, mean speed is u given 298, cp we know for this temperature is 1148 Kelvin. Okay, let's write down, because don't mention all these things, just write down the cp as this. Okay, that's better. So is equal to 1148 into 144 divided by 298 square. Okay. If you solve it, you will get the value was 1.8615, and this is your answer. Okay. So let's go to the next question. The blade holding coefficient psi, we just get it 1.865. So next question is the pressure ratio of the stage. Okay, so pressure ratio of the stage we need to find out. Okay, so now in this question we need to find out the pressure ratio of the stage. Okay, so in the question, if you see, it's mentioned that with the inlet temperature of 1100 Kelvin and the pressure of 3.4 bar. Okay, that means the inlet temperature they mentioned as 1100 Kelvin. Okay, and that temperature is also going to be same for the second stage. Stator and nozzle, there won't be any temperature change. Okay, there will be only temperature change in the rotor stage. Okay, so, and that temperature difference also we know it. Okay, so that means it will be now easy, because we know T02 is equal to T01 is equal to 1100 Kelvin, and delta T0 is equal to T01 minus T03. Okay. So yes, but we need T03 because T03 is the unknown. So T03 is equal to T01 minus delta T0. So T01 is 1100 Kelvin minus delta T0 in the question. It's mentioned the temperature drop across the stage. The total temperature drop across the stage is 144 Kelvin. Delta T0 already given 144. Okay, you solve, you will get it is as T03 as 956 Kelvin. Okay. So now we have a T03. That means we can now calculate the isentropic efficiency of the turbine in between T01 and T03 stage. Isentropic efficiency always relates to the actual temperature difference divided by the isentropic temperature difference. Okay, which is T01 minus T03 divided by T01 minus T03s. Okay. Okay, you can solve it. which is delta T naught divided by T naught 1. You take common, it will be 1 minus T naught 3H divided by T naught 1. You can convert it into isentropy relation of pressure, temperature and pressure. Then it will be P naught 3 by P naught 1 to the power gamma minus 1 by gamma. So, but in the question what it asked, okay, in the question it asks the pressure ratio of the stage. Okay, pressure ratio means this P naught by P naught 3 by P naught 1 we just need. Okay, just take it to the left side, P naught 3 by P naught 1, and all other things just convert and put in the right side. Okay, if you do that, you will get this expression P naught 3 by P naught 3 by P naught 1 is equal to 1 minus delta T naught by eta T into T naught 1 to the power gamma by gamma minus 1. Okay, because all the things known. Okay, and the isentropic efficiency of the turbine given as 0.9. Okay, so eta T is what? 0.9. Okay, so just substitute all these values. T naught 1 is 1100 Kelvin. Okay. Okay, so then 0.4 by 1.4. Okay, sorry, 1.4 by 0.4. Okay, you will solve, you will get the value as 0.533. Okay. Okay. Okay, but in the question it's mentioned the pressure ratio of the turbine means always take from 1 to 3, not 3 to 1. Okay, just take the ratio. Okay, so P naught 1 by P naught 3 is equal to your pressure ratio of turbine stage. Okay, is equal to 1.875. Okay, This is your second bit answer. Second bit or B? B. This is the answer of your A. So this is the B bit answer. Okay. So in the question also it's mentioned the initial temperature given, the total pressure of 3.4 bar. That means P01 already given 3.4 bar. Just substitute there in this ratio P01 by P03 and find out the P03 temperature. Sorry, pressure. So P01 is equal to 3.4 bar. So P03 is equal to 1.813 bar. So what is next question? What is the flow angle? Okay, second bit also done. The next bit is flow angle. We need to find out the flow angles. Okay, so before calculating this C bit, there is one very important thing which to be noted in the question is that if in the question they mention if the convergent nozzle is operating under the choked condition. Okay, if the convergent nozzle is operating under the choked condition, determine this. Okay. So in the question actually we see that the convergent nozzle is operating in the choked condition. Then what does it mean? How it will help in finding the flow angle. So okay. So the nozzle. So nozzle is choked. It means that your exit Mach number is equal to 1. Okay, so this is the important thing you need to remember in the question. If it is asked the nozzle is choked means what will be your Mach number? It will be the equal to 1. Okay, on the sonic velocity. Okay, so that means we can now calculate all these velocities. Okay, so C2 is equal to square root of gamma r t. Okay, so and T02 by T01 is equal to gamma plus 1 by 2. You solve it, you will find it is 1.165. Okay, sorry, it's T02 by T2. Okay, so but we know already T01 equal to T02 equal to 1100 Kelvin. Okay, then from this above expression we can find out the T2 value. Okay, what is the static temperature at the nozzle exit? The static temperature at the nozzle exit T2 is equal to 944.2 Kelvin. Okay. Okay. So, okay. So in this expression, when you put now, okay. So when you put all these thing in this expression, you will find out the C2 value also. The C2 value is also, if you calculate, it is 600.3 meter per second. Okay. Because gamma, you know, R you know, okay, and T2 now you find out. Okay, that means you can find out C2. Okay. So okay, next we find out the axial velocity. Okay. Axial velocity CA is equal to U into phi. Okay. Phi is your flow coefficient, okay, which is 0.95 given, and the mean blade speed is 298, which is U also given. Okay. So which is your 298 into 0.95. Means your axial velocity CA will be 283 meter per second. Okay. Okay, so now if you see the second stage velocity triangle where alpha 2 is mentioned, because at the end we need to find out this alpha okay, alpha 2, alpha 3, all these things we need to calculate. Okay, so all the flow angles means we need to calculate. Okay, for all stages, okay, 2 and 3. Okay, so yeah, so if you see alpha 2, the whatever the perpendicular line is the your CA, okay, vertical velocity, and C2 is your and C2 is the diagonal. Okay, so if we can calculate the cos alpha 2, and the cos alpha 2 will be your what, CA by C2. Okay, okay, because axial velocity divided by the C2. Okay, from velocity triangle, the cos alpha 2 is equal to CA by C2. Okay, now CA we find out here above 283, C2 we also find out from here 600.3. Okay, so if you solve, you will get 0.47. Always remember this is in so cos alpha 2, so just find out also alpha 2 in degree. So alpha 2, if you find out, it will be 62 degree. Okay, this is your answer. Okay, again let's find out also beta 2 similarly. So we know one relation. This relation always helps when you know alpha 2. How do you calculate the beta 2? Okay, this expression always helps. Okay, not also beta, for any kind of things, alpha in between the it is the relation between the alpha and beta for any kind of states. Okay, so yeah, so it will be u by ca is equal to tan alpha 2 minus tan beta 2 is equal to 1 by 5. Okay, this is a very important relation. This relation can be also asked as a question. Okay, so tan, because we need beta 2 anyway, tan beta 2 is equal to tan alpha 2 minus 1 by 5. Okay, because alpha 2 we already know, phi also we know. Here phi already given in the question, 0.95. Okay, so you will solve it, you will get this value as 0.828. Okay, and the beta, if you solve for beta 2 is your 39.6 degree. Okay, this is your answer. Okay, so now we have beta 2. Okay, so now next we need to calculate the same way alpha 3 and beta 3. Okay, so okay, we know one thing, that is the turbine specific work is equal to Wt is equal to Cp into delta T naught. Okay, if you solve, you can just get in other way, U into Ca into tan alpha 2 plus tan alpha 3. So from here we can actually calculate this tan alpha 3. Okay, so if you take tan alpha 3 on one side, tan alpha 3 is equal to Cp delta T naught divided by U into Ca minus tan alpha 2. Okay, so it is 1148 into 144 divided by 298 into 283 minus 1.8807. Okay, all these values are given, just substitute and find out. Okay, you solve it, you will get 0.0793, and if you actually solve it, you will get the alpha 3 as 4.54 degree, which is your answer. Similarly, you can calculate also your beta 3 from the well-known expression of which will relates your beta 3 and alpha 3. I already tell you, the U by Ca is equal to tan beta 3 minus tan alpha 3. Okay, so what is tan beta 3 then? Tan beta 3 is equal to 1 by 5 plus tan alpha 3. Okay, so if you solve, put everything, you will get this value as 1.132. Okay, so beta 3 is equal to 48.54 degree. Okay, so this is your answer. Okay, so we calculate all the bits flow angles. Okay, all the flow angles also we calculated. Okay, okay, so beta 3, alpha 3, beta 2, alpha 2. Okay, all the angles we calculate. Okay, we also calculate the pressure ratio P01 by P03 and your the blade loading. Okay, okay. Blade loading coefficient. Okay, so with this we'll end the section. So thank you very much for attending the section. If you have any doubts related to any of the sections, you can ask in the corresponding sections, comment sections in my YouTube channel, Sumit Sagar Hota. Okay, my name that is the YouTube channel name also. Okay, same as the YouTube channel name. You can ask in those comment sections. Okay, for this comment summary section, if there is any doubt, you can ask. Okay, and any other doubts, you can ask in the regarding the assignments and all those things. You can ask in the forum. Okay, question and answer forum of the NPTEL. Okay. So this is the last section of this course. Okay, for this semester. Okay, so keep learning and have a nice day and good night and goodbye.